Hello everyone and welcome back to the video lecture series for Calculus 1. Today we are going to be covering the derivatives of trig functions. So before we get into the derivatives of trig functions, we actually need to backtrack a little bit back into limits and cover two special limits that deal with trig functions. So the limit as x approaches 0 of sine of x over x is actually equal to 1. And the limit as x approaches 0 of cosine x minus 1 over x is equal to 0. Now this limit here, sine x over x, the limit as x approaches 0 of sine x over x equals 1. This rule will always apply if whatever is inside of your sine function exactly matches what is in the denominator. If whatever is inside of the sine function does not exactly match what is in the denominator, you can't use this limit, but you might be able to do some algebraic manipulation so that you can use that limit. So we're going to evaluate the limit as x approaches 0 of the sine of 4x over x. So unfortunately, this looks very similar to sine x over x, but it is not exact because what is inside the sine, which is this 4x, is not exactly the same as what is in the denominator. Now, anything inside of a sine, you cannot touch it. So you cannot just simply divide this by 4. That 4x is inside of the sine function. You are stuck with it. But you can easily make the denominator match what is inside the sine function by multiplying it by 4. The only thing is you can't just multiply this by 4. Whatever you do to the bottom of a fraction, you need to do the exact same thing to the top. Also, this 4 that I have just multiplied to the numerator is a constant multiple, so it can come out of the limit altogether, and we're going to write this as 4 times the limit as x approaches 0 of the sine of 4x all over 4x. So now that what's inside the sine exactly matches what is in the denominator, its limit is going to equal 1. So this entire limit right here is going to equal 1, giving us a limit of 4 times 1, giving us a final answer of 4. Now for this next one, we're going to do something very similar. You can do pretty much whatever you want to a fraction as long as you do the exact same thing to both the top and the bottom. So we're going to be using this first limit here as x approaches 0 of sine x over x is equal to 1. The problem is with this that we have sine of 3x over sine of 5x, so neither of these are divided by x. So again, as long as you do the exact same thing to both the top of a fraction and the bottom of a fraction, you can do almost anything you want. So what I'm going to do is I'm going to take both the top and the bottom, and I'm going to divide both of these by x. So I'm going to take the sine of 3x in the numerator, and I'm going to divide it by x. And I'm going to do the same thing to the bottom. I'm going to take the sine of 5x in the denominator, and I'm going to divide it by x. I didn't actually change anything because I just divided both the top and the bottom by the same thing. And unlike derivatives, you can take a quotient inside of a limit and simply write it as a quotient of two separate limits. This isn't a derivative, so we can do this. So I'm going to write this as the limit as x approaches 0 of the sine of 3x over x. And then I'm going to divide it by the limit as x approaches 0 of the sine of 5x over x, just to make this a little bit easier to work with. So then again, if what is inside your sine exactly matches what is in the denominator, you can go ahead and use that limit. So sine of 3x, remember we are stuck with that 3x because it's inside of a sine, does not exactly match what's in the denominator. So I'm going to fix that by multiplying both the bottom and the top by 3. Then I'm going to do the same thing over here. I have sine of 5x over x. I'm going to make the denominator match what's inside the sine by multiplying it by 5. And whatever you do to the bottom, you need to do the exact same thing to the top. Also, this constant multiple of 3 can come out of this limit, so I'm going to write this as 3 times the limit as x approaches 0 of the sine of 3x all over 3x. Then we are going to divide it by, I'm going to take this constant multiple of 5 and write it outside of this limit. So we're going to divide it by 5 times the limit as x approaches 0 of the sine of 5x over 5x. Now for each of these limits, now that what's inside the sign matches the denominator, each of those limits is equal to 1. So we have 3 times 1 divided by 5 times 1 gives us a final answer, a final limit of 3/5. Now you might be wondering what that has to do with the derivatives of trig functions. So the reason why the derivatives of sine and cosine work out the way they do is because of those two special limits. So there are 6 trig functions, but you really only need to memorize the derivatives of 2 of them. The derivative of sine x is equal to cosine x, and the derivative of cosine x is equal to negative sine x. Here's why. So if you were to use the limit definition to actually find the derivative of the sine function, you would get the limit as h approaches 0 of sine of x plus h minus the sine of x all over h. Sine of x plus h is there. You can rewrite this using a sum and difference trig identity. It can be written as sine x times cosine of h plus cosine x times sine of h all over sine of x. And then a little bit of factoring by grouping, rewriting later. You can rewrite this as the sine of x times cosine of h minus 1 plus cosine of x times sine h. So we're going to rewrite the numerator as the sine of x times cosine of h minus 1. And you are allowed to split up addition inside of a numerator. So we are going to add to it a totally separate fraction, cosine x over sine h, both of those fractions over the common denominator of h. So then if you take the limit as h approaches 0 of each of these, remember the limit of h approaches 0 does not affect anything to do with x. So sine x is considered a constant multiple and can come out of the limit as h approaches 0 of cosine h minus 1 over h. Then plus this cosine of x, which has nothing to do with h, can come out of the limit, and then times limit as h approaches 0 of sine h over h. So this limit here is equal to 0, and this limit here is equal to 1, so that reduces it down to the derivative of sine x is equal to cosine x. So the proof of why the derivative of cosine works out the way it does is very similar. Now, why do you only need to really memorize these two? Because every other trig function can be written in terms of sine and cosine, if you are stuck and you don't remember the derivative of, let's say, tangent, you can always rewrite it in terms of sine and cosine and use quotient rule to figure out its derivative. Now, that will take a while, and we're actually going to do it in the next problem. So for speed purposes, you may end up just memorizing them anyway. I will highly recommend you memorize the derivative of tangent because we actually use tangent all the time in application problems. Sine, cosine, and tangent are really the big 3 that you really need to memorize because realistically, in any application problem, anytime that you need to set up a trig ratio, you're really only going to use sine, cosine, or tangent. There's really no reason to use the other 3, even though you will be seeing the other 3 on your homework and maybe on an exam. So if you're in a pinch and you don't remember the other trig functions, as long as you remember sine and cosine and how to write the other trig functions in terms of sine and cosine, you can always figure out what their derivatives are using quotient rule. So we're actually going to do that for the derivative of tangent x. So I'm going to first rewrite tangent as sine x over cosine x. And I'm going to use the quotient rule to figure out its derivative. So using quotient rules, sine x is going to be the top function, cosine x is going to be the bottom function. So with quotient rule, you start off with the bottom function left alone. Then we're going to multiply it by the derivative of the top function, so we will multiply it by the derivative of sine x. Then we are going to subtract the top function left alone. times the derivative of the bottom function, so times derivative of cosine x, all over the bottom function, cosine x squared. So then let's just take each of these derivatives. So I have cosine x times derivative of sine is cosine. Then minus sine x times the derivative of cosine x is negative sine x. All over the bottom function squared, which you can either write that as cosine x parentheses squared, or you can write it as cosine squared x. Doesn't really matter. These two mean the exact same thing. So then I am going to just do a little bit of simplifying in the numerator. So cosine times cosine is cosine squared. And then negative times a negative is a positive. Sine x times sine x can be written as sine squared x, all over cosine squared. Now you cannot cancel out the cosine squareds because of that plus sign in the numerator. But cosine squared plus sine squared, that should look familiar. That's actually the Pythagorean identity. Cosine squared plus sine squared is equal to 1. And then, what other trig function is 1 over cosine? Well, 1 over cosine is secant. So 1 over cosine squared x can actually be rewritten as let's try that again. It can actually be rewritten as secant squared x. So that is the derivative of tangent. So these are the derivatives of the 6 trig functions, and I am going to post on Canvas a derivative rules sheet that gives you not only the derivatives of all 6 trig functions, but the derivatives of pretty much every trig function, or every function in general that we are going to be covering in this course, and even beyond. So I'm going to post that derivative rules sheet on Canvas, and you're going to look for that in the Canvas module, but these 6 will be on it as well. So what we're going to do is we are going to find the first derivative, dy dx, of sine x times x cosine x. I will say that there is hidden multiplication right there between the x and that cosine x, so this is going to need product rule. So let's find its derivative. So its derivative, which is dy dx, equals derivative of sine x is cosine x, minus, now since the product rule is going to involve more than one term, and those two terms are following a minus sign, please use parentheses because that minus sign is going to need to get distributed to both terms. So we're going to start with the derivative of the first part of the product. Derivative of x is 1, times the second part of the product left alone, cosine x, plus the first part of the product left alone, x, times the derivative of the second part of the product. Derivative of cosine is negative sine. So then distributing that minus sign, we're going to get cosine x minus cosine x, and then minus minus is plus x times sine x. So then cosine minus cosine cancels each other out, leaving you with x sine of x as your final answer. So we're going to do this same thing. We're going to find dy dx for this next function here, 1 plus sine x over 1 minus sine x. Do not cancel out the sine x's and do not cancel out the 1's. Those are common terms, not common factors, and common terms do not count. So you cannot cancel anything out across the plus sign or the minus sign. What we're going to have to do to find this derivative is we are going to need quotient rule for this. So using quotient rule, 1 plus sine x is the top function, 1 minus sine x is the bottom function. So we're going to start with the bottom function left alone, 1 minus sine x. Then we're going to multiply it by the derivative of the top. So derivative of 1 is 0, derivative of sine x is cosine x. Then minus, we're going to take the top function and leave it alone, 1 plus sine x, times the derivative of the bottom function. So here we go. Derivative of 1 is 0. Leave the minus sign where it is. Derivative of sine x is cosine x. all over the bottom function with parentheses around it, 1 plus sine x, parentheses squared. So then let's do some distributing, and remember, we're going to leave the denominator alone. We're just going to focus on simplifying the numerator. So cosine times 1 is cosine x. Cosine x times negative sine x is minus sine x cosine x. And then minus will turn into a positive. Cosine times 1 is plus cosine of x. And then cosine times sine is plus sine x cosine x. All over the bottom function, 1 minus sine x, parentheses squared. Remember, with quotient rule, we're going to leave the denominator alone. Then in the numerator, minus sine x cosine x plus sine x cosine x cancel each other out. And then we can combine these terms. Cosine x plus another cosine x is 2 cosine of x. All over, parentheses, 1 minus sine x squared. And that is going to be your final answer. So for this next one, we are going to find the first derivative dy dx of e to the x times cosine of x. So because there is multiplication here, this is going to need the product rule. E to the x is the first part of the product, and cosine x is the second part of the product. So we're going to start with the derivative of the first part of the product, which is e to the x, times the second part of the product left alone, cosine x. Then we are going to add to it the first part of the product left alone, e to the x, times derivative of the second part of the product, derivative of cosine is negative sine. And this really doesn't simplify very much. If you want to factor out at e to the x and write it as e to the x times cosine minus sine, you can. It doesn't really simplify any further than that. So because the other three trig functions are course objectives, let's work with some of the derivatives of some of the other trig functions. So we're going to find the first derivative dy dx of secant of x times cosecant x. So because this is multiplication, this is going to need the product rule. So secant x is the first part of the product. Cosecant x is the second part of the product. So we're going to start with the derivative of the first part of the product. We're going to start with the derivative of secant x. Then we're going to multiply it by the second part of the product, cosecant x left alone. Then we are going to add to it the first part of the product left alone, secant x. And then we're going to multiply it by the derivative of the second part of the product, derivative of cosecant x. So derivative of secant x, like we covered a few slides ago, is actually secant x tan x. And then times cosecant x. Then we're going to add to it secant x times derivative of cosecant x is actually negative cosecant x cotangent x. Now for simplifying purposes, this technique doesn't always work. So, if you tried to use this technique on, other types of products that look like this, it may or may not work. But one thing that you can do, because we have an awful lot of multiplication of functions that can be written in terms of sine and cosine, if we write all of these in terms of sine and cosine, we might be able to get some things to cancel out. And I stress the word might because this doesn't always work. It really depends on what kind of combinations you have of the other trig functions, but it's worth trying and seeing if it helps. So I'm going to write secant as 1 over cosine x times, I'm going to write tangent as sine x over cosine x. And I'm going to write cosecant as 1 over sine x. Then positive times a negative is minus. And I'm going to do the same thing for this next product. So secant is 1 over cosine. Cosecant is 1 over sine. And then cotangent is cosine over sine. And then any common factors in the numerator and denominator can cancel out because there's multiplication. So the sine x and sine x can cancel each other out because there's multiplication. When they cancel out, they become 1. And then same thing over here, cosine can cancel each other out because there's multiplication. So then let's multiply what's left over. 1 times 1 times 1 is 1, over cosine times cosine is cosine squared. Then minus, numerator is 1, sine times sine is sine squared. And then 1 over cosine can be written as secant, so this can be written as secant squared. Minus 1 over sine is cosecant, so I'm going to write this as cosecant squared. And there's really no identity for this, so we're going to call that good enough. Now for higher order derivatives, like I said in the higher order derivatives video, polynomials, their higher order derivatives will eventually go off to 0. Higher order derivatives for, e to the x just never stops and is always the same. There is a pattern to some of the higher order trig derivatives. So what I want you guys to do is I want you guys to take y equals sine x, and I want you guys to find the first 4 derivatives and see what happens. So just take a few minutes, pause the video, and look for patterns with the first 4 derivatives. All right, so the first derivative of sine, is cosine. Then for the second derivative, which is the derivative of the derivative of cosine is negative sine. Then the third derivative, which is the derivative of the second derivative, leave that minus sign where it is. Derivative of sine x is cosine x. Then the derivative of negative cosine is negative sine, which is back to sine x. So you notice by the fourth derivative, we are back to the original function. And with sine x, this will happen. The higher order derivatives will eventually repeat themselves. And the same thing is going to happen with the higher order derivatives of cosine, because cosine is going to cycle through pretty much the same way sine did. However, that is not going to happen with the other 4 trig functions. So let's take the function cosecant x, and we're going to find the second derivative. So let's start with the first derivative. So the first derivative, dy dx, the derivative of cosecant x is negative cosecant x times cotangent x. Now here's the reason why the higher order derivatives for cosecant are not going to just repeat themselves like sine and cosine. That product right there. You're going to need product rule to find the second derivative. So the second derivative, d squared y over dx squared, we're going to call negative cosecant x the first part of the product, and we're going to call cotangent x the second part of the product. So we're going to start with the derivative of the first part of the product. We're going to start off with the derivative of negative cosecant x times the second part of the product, cotangent x left alone. Then plus the first part of the product left alone, negative cosecant x. Then times the derivative of the second part of the product times derivative of cotangent x. And then let's take these derivatives. So the derivative of negative cosecant, again, the derivative of cosecant is already negative, so negative times negative is going to give us a positive cosecant x, cotangent x, times another cotangent x, and then plus negative cosecant x times the derivative of cotangent is negative cosecant squared x. And I'm going to save you guys the trouble. Even if you were to rewrite all of these in terms of sine and cosine, that's not going to work here. You're not going to get things to cancel out like we did over here, just because of the nature of what trig functions we had. But one thing that you can do is you might notice that there is a cosecant in both of these terms. There's a cosecant here, and there's a whole ton of cosecants here. So one thing that we could do is we could factor out a cosecant x. So what's left over in the first term, cotangent times cotangent is cotangent squared. And then negative times a negative is a positive. cosecant squared is what's left over in the second term. So that's really all you can do, and that's really as simplified as it gets. So you can actually imagine that the third derivative is not going to cycle through. And the third derivative we're not actually going to do because that involves something called the chain rule, which is going to be in the next video. So thank you all very much for watching, and I will see you guys in the next video. Bye-bye.